Hi, my name is Rebecca Holman, and this is The Physics of Breakfast, a speech given by Peter Juncker. This feels something that's dissolved in solution does not give a uniform stain. There is a darker ring around the edge, and this is called the coffee ring effect. When hot water enters coffee grounds, it extracts oils and small molecules, and these pass through the coffee filter. Oils extracted from the coffee bean are water-soluble, so they do dissolve in a cup of hot water, and this means that coffee is a solution. To test the physics of the coffee ring effect, Professor Juncker made a model of coffee using the suspension of colloidal particles, which are micron-sized plastic spheres, in water. These particles follow the flow of water molecules as the drop dries, and so it traces out the flow of water. When you put a drop in a microscope and watch it dry, you can see the edge of the drop become darker as more and more particles pile up there. The individual parts can be tracked with a microscope as particles are pushed from the middle of the drop to the edge of the drop, where they line up and jam into dense packing and form the coffee ring effect. Surface tension is created because molecules are cohesive in nature and are attracted to each other. This means the molecules in the interior of the drop are happy because they are next to lots of other molecules, but the molecules on the surface of the drop aren't next to as many as they could be. Surface tension minimizes surface area, so the most amount of molecules are happy, and in three-dimensional space, a sphere minimizes surface area, while a droplet of liquid forms a sphere on a surface. Molecules are also attracted to the surface they are sitting on, so adhesive force wants to spread the drop out as thinly as possible, so it interacts with the surface as much as possible. The cohesive and adhesive forces compromise to form a spherical cap. As the spherical cap dries, the volume decreases, but the edges of the drop become pinned in place, so the drop doesn't dry from the edge in. The diameter remains the same as it dries, and instead the drop flattens down from the top until the last stage of drying, where the edges depin and evaporation finishes. Therefore, the coffee ring effect is just a happy accident that is caused by the edges of the drop being pinned and surface tension, because water in the middle gets pushed to the edge, and this water carries dissolved solutes to the edge, which makes it appear darker. Normally, when you add heat to an object, you go from a more solid-like to a less solid-like state. But when you take raw eggs and heat them to make scrambled eggs, they harden. So this makes it seem that heat makes eggs go towards a more solid state. To test this, a universal testing machine was used, and a UTM creep test was run. This distinguishes between something that's solid-like and something that's liquid-like by applying a force down to hold a plate still on the object in question. A spring, for example, would require an applied force to compress it that would give a constant line when you plot force versus time, because it depends on how much you compress it and not on time. If you press a plate down in water, there will be a force that resists it, and if you hold the plate still, the resisting force will decrease with time, and eventually, if you wait long enough, the resisting force will fall to zero. For scrambled eggs, there was a little bit of decay of the resisting force, but it reached a plateau. So this was an elastic response, and shows that scrambled eggs are in a solid-like state. For raw eggs, the resisting force decayed to zero, so this shows that raw eggs are in a liquid-like state. So if scrambled eggs are more solid than raw eggs, why does heat make eggs more solid? This is because eggs are 10% protein in solution of water. Proteins have hydrophobic and hydrophilic regions, so the protein folds to keep the hydrophobic regions in the interior of their protein isolated from water, and the hydrophilic regions on the surface of the protein interacting with water. Heating denatures proteins so they unfold. When the protein tries to fold again after denaturation, they misfold, and the different hydrophobic and/or hydrophilic regions of different polypeptides end up sticking together and give a stiff aggregation of proteins. This aggregation of proteins is what makes scrambled eggs harder than raw eggs. Have you ever noticed that the last few pieces of cereal end up clumping and sitting next to each other instead of being uniformly dispersed throughout the bowl of milk? This is because molecules in fluid are attracted to a solid and form a meniscus. Cereal is less dense than the milk it's sitting on, so it wants to sit as high as it can above the milk. This results in a meniscus that slopes upwards towards the cereal, so the cereal sits as high as it can. When two pieces of cereal are sitting on the surface of milk and happen to bump into each other, they each have an upward meniscus, and they end up climbing up each other's meniscus, and this decreases potential energy as they come together. They both want to get to the highest point, so that if they climb up each other's meniscus as well as their own, they will end up higher up from the milk and with less potential energy. So this is what causes the pieces of cereal to come together in the bowl of milk. One interesting thing I learned as a result of this lecture was an application of the coffee ring effect. One of these applications is a simple and affordable diagnostic tool for testing malaria and Alzheimer's in regions where you may be far away from hospitals. A sample of blood is mixed with a reagent and left to dry. You can then look at the spot left behind to determine if the patient has malaria because of the coffee ring effect. This is not in use currently, but has major implications for the future since it is inexpensive. All you need is a flat surface and the reagents, and it can be administered by essentially anyone. You don't have to be near a hospital, or you don't have to be a doctor to give the test or read the results. One idea not discussed by the speaker that interested me was the physics of protein folding, since I'm a biology major, and this shows how all sciences are interrelated. The Leventhal paradox discusses how proteins fold. Leventhal's paradox was suggested because proteins were found to refold from a disordered state in seconds. If the protein were to sample random configurations in order to reach its energy minimum, even for a short protein chain, it would have to test 10 to the 30th conformations. Therefore, it can be assumed that, due to the speed at which proteins fold, a pathway must exist in order for a protein to fold quickly without error. The thermodynamic hypothesis says that the native state of the protein exists as the state in normal physiological conditions, which minimizes its Gibbs free energy. This means that the native state is a unique minimum determined by the protein's amino acid sequence as well as the environment it is in, regardless of the energy bestowed to the protein. The kinetic hypothesis is the exact opposite view. It predicts that the native state is not at a total energy minimum, but it is actually at a local minimum, which is determined by the folding pathway, which achieves a low free energy the quickest. Misfolded proteins, which form amyloid fibrils, are extremely dangerous to physical and mental health. Most notable are the neurodegenerative diseases which arise from misfolded proteins, such as Alzheimer's disease, caused by amyloid beta protein, Parkinson's disease, and Creutzfeldt-Jakob disease. Amyloid fibrils are not individual misfolded proteins, but are aggregates of the same misfolded protein. All amyloid fibrils, independent of the misfolded protein forming them, are mostly beta sheet structure. Therefore, even for predominantly alpha helical proteins, when forming amyloid fibrils, they will go through an alpha helix to beta sheet transition. This mechanism proposes that the aggregation of the proteins and the formation of the fibril arises from proteins in their intermediate molten globule state. This means that they are not completely denatured, but are more free-form with some secondary nature. When left in that form, the proteins will aggregate to form a large beta sheet structure to reduce free energy, creating an undefined branch structure from the leftover parts of the chain not used in the sheet, and therefore forming amyloids.